Good afternoon. Today it is the last seminar of this year, and we have the great pleasure to welcome Professor Richard Elliott. He's currently a professor emeritus at the Chemical, Biomolecular, and Corrosion Engineering program at the University of Akron. Among his research interests, we can highlight thermodynamics of hydrogen bonding, molecular simulation, perturbation theory, and integral equation theory, experimental phase equilibrium measurements, and chemical reaction engineering. Besides, he's the co-author of the thermodynamics section of Paris Chemical Engineering Handbook and also the co-author of the sixth edition of Properties of Gases and Liquids. Once again, thank you so much for being here, Professor Elliott. Welcome, and please feel free to start presentation.
I'm not going to be able to convey as much profound information today as I might normally hope to, but I do appreciate you giving me the privilege of speaking to you today. What I'm going to talk about, for the most part, has to do with self-diffusivity, and the connection to the adventure continuing is that we didn't get to spend as much time on the last few chapters as we spent on the earlier chapters. Hopefully that makes sense. And so chapter 12 is the penultimate chapter, the next from the last. And then chapter 13 about surface tension is of the last chapter. And so both of those chapters need to be a little bit updated even now. But in general, I think it's safe to say that people don't stop developing models in between the years that the properties of gases and liquids gets published, right? Especially if it's 20 years. And so I'm hoping it's not going to be 20 years the next one. I'm aiming for 7. It might end up being 10. So what do we do about those intervening years? We can't just ignore what's going on. We need a way of accommodating those new developments. And so not sure what the final result of that's going to look like, but if there's a new method that's out that seems to be better, I want to do something to make sure that everybody knows about that. And so lately, people have been doing a lot of work correlating transport properties with residual entropy. Didn't get a chance to evaluate that. Let's evaluate that now. And I have a couple of pet peeves in the way that I approach this. One is that I see a lot of people correlating the transport properties using the Enskog limit for hard spheres as their basis. And that just gives me some pause because there's a lot of molecules that are not spherical. Most of them are not spherical. And so maybe you could get away with that sometimes, but sooner or later, that's got to get you in trouble. And so I hope to expose a little bit about where that boundary is when you might start to get in trouble. And so I'll talk about what is the foundation of this Enskog limit. There's also a couple of other perspectives on what happens at high density and low density. And those have been articulated by Rosenfeld, who really innovated this entropy scaling concept. Zugatov came around a few years later and said, well, maybe it shouldn't be like that. It should be like this. We'll talk about what that is. Recent correlations using residual entropy have been developed for all the transport properties, really, by Ian Bell and his collaborators and by Jean-Noël Joubert, also other workers, but the others have not been including self-diffusivity in their analysis. So that's why I'm going to focus on just these two. This goes along with some work that we did using molecular simulation of non-spherical molecules. So maybe you can guess or anticipate, why I'm trying to get away from this Chapman-Enskog for spheres limit, and I've been working at that for a while. Can we implement that finding in a way that's basically just as easy to use as the Chapman-Enskog result, but incorporates a little bit more reasonable physics? And I think we can. The baseline for comparison is this LSM model, which we found to be, in the analysis we did, to be the best available model. And it's essentially a free volume model combined with a little bit of corresponding states. And it's essentially equating every molecule in the world to the Lennard-Jones spheres. And you gotta give some credit. It fits the data pretty well if you give it enough parameters, okay? So that's our baseline. The Elliott model from 2010 was very close to this LSM model, but not quite as good, and it had more parameters. At that point, I want to articulate a general model for entropy scaling, and then to back out of that general model which terms are absolutely essential, and to reduce that model down to what fits the data at this moment. And that's the stepwise backward regression. And I'll use the basis of something called the Bayesian information criterion for doing that backward regression. This BIC method has become a lot more popular. You'll see it in the machine learning discussion and literature nowadays, but it's actually been around a long time. I used it in 2008 when I was trying to figure out the best intermolecular potentials for the SpeedMD model. And so it's got some use beyond machine learning. Just be aware of that. So we'll start with alkanes, then we'll generalize to non-alkanes, and then we'll come to some conclusions about which scaling methods are the best. So just reviewing what the Chapman-Enskog limit says is, well, even before Chapman-Enskog, I think, they had this low density limit, which is just essentially the translational energy of the atoms in the low density limit. And then Chapman and Enskog came along and they said, well, we can improve that to go to higher densities by recognizing that the contact value of the radial distribution function for spheres, again, hard spheres, changes as you go to higher density. And remember, these are all hard spheres. That's all that they've got. And so then Rosenfeld came along with his entropy scaling theory, and his proposition was that the self-diffusivity ought to go according to this sort of like mean free path of the ways that the molecules interact. And that led to this slightly weird scaling that you might be able to guess is going to cause a problem in the low density limit, and it does. So this was his argument. Zugatov came around a few years later. I thought I had the year here. I left it off. It's somewhere around 95 or 93, something like that. Or 85, 83. That's what I mean. What he said was that the probability of a molecule diffusing is roughly equal to or proportional to how much the fluctuations are through the entropy. That's how probable it will be that the molecule can jump out of its cage and move to a different cage and systematically keep percolating along through the fluid. He developed that perspective for liquids, and then it just leads to same scaling all the way through all the different densities. And so he ends up with this log of this ratio of diffusivity. So this is the low density limit. This is the diffusivity at any density, okay, is a function of the residual entropy, polynomial and residual entropy. One thing I want to mention here is this goes back to even the low density limit for hard spheres, that the density times the self-diffusivity, mass density, is going to have units of grams per centimeter second. Okay, so that number will be a finite value even at zero density. So as we do our molecular simulations and we want to understand what's happening at all densities, what we need to plot is not self-diffusivity. What we need to plot is density times self-diffusivity, and then we will be able to see the y-intercept. So reviewing a little bit more of history here, around about 2015, Gross and co-workers said, well, it helps if we put a scaling parameter here in the denominator. And the scaling parameter they used, can you guess, was the M of the PC shaft, right? So the effective number of segments of a tangent sphere's chain. And they were doing that correlation for viscosity. And when it came to their reference viscosity, they chose the Chapman-Enskog for spheres. I think it was Lennard-Jones spheres in this case, because they're using this collision diameter for Lennard-Jones parameters. But it's not too clear how they're treating the attractive effects here. I think this G of sigma is coming from the Chapman-Enskog for hard spheres. Okay, fast forward a little bit and then talk about the entropy scaling method for self-diffusivity. And Bell and coworkers came up with what amounts to a switching function called W that goes from their low density limit up to the liquid range where we can recover this polynomial. They did not take the log over here. So that's a little different from what Zugatov said. What they did to fix the low density limit was they said, well, the residual entropy to the 2/3 power in the low density limit becomes the second virial coefficient to the 2/3 power. And since the second virial coefficient has a density in it, and that's to the 2/3 power, the 2/3 power on the residual entropy in the denominator will cancel with that row, and we'll be back to a function that is finite value at low density. And they call that plus scaling. The key is to use this switching function, and the switching function is a kind of like, imagine a tanh function that just kind of is one value at one range, another value at the other range, smoothly. Deleuze and Joubert, and another number of authors there, what they said was, let's set this scaling parameter equal to the critical value of the residual entropy. So now it becomes something like a corresponding states method that is also an entropy scaling method. And they didn't write it this way, but essentially what they had was a switching function that goes from the low density limit to the high density limit. They did include the log function here. They also included, let's see if I can, oh, that didn't work. Here, I wanted to highlight that. So they included this parameter here, this variable, that is essentially a lumping of the residual entropy with the log of the residual entropy. So what's going to happen as the residual entropy goes to zero? You're going to have this log here, and that's what this quantity is going to go to. And so the log of zero is diverging, so this better diverge, and we better be careful about that. All right, so and that's a way of incorporating this Rosenfeld scaling in the low density limit. So this I'm just going to call it the GBP method from now on, and something to look out for with that method. Well, a day without statistical mechanics would be like a day without sunshine, right? So we have to show some sort of stat mech here. And so if we want to do a molecular simulation and get some transport properties, it's absolutely the easiest one is the self-diffusivity. All these other properties, they involve derivative functions of things that are very difficult to get good statistics on. And so if you read about how you calculate the viscosity in these various methods, you really have to run many simulations over and over again. They can be somewhat short simulations for viscosity, but you have to run hundreds to get a good average of what the property actually is. With self-diffusivity, one's good enough. You just track it a little longer. Maybe you do some block averaging. So that's why that's a special attraction to me for self-diffusivity. And if we can't understand the easy one, maybe we're not ready to take on the more complicated ones. I say that with a grain of salt because these methods for calculating viscosity by simulation, they're getting pretty good now. And people are getting good reproducible results that compare well to experimental data. So, and I've gotten some of those myself. So maybe we're ready for discuss. So what kind of results do we get when we do these molecular simulations and we want to extrapolate them to the low density limit? What you see is we do get a finite limit. It's kind of a small number, okay? But it's a non-zero number. And this blue curve represents what happens with methane, all right? And you can see that the self-diffusivity is ending here at about 0.5 grams per cc. Well, why is that? Methane freezes at this density. And so essentially what we're getting to is a jamming density. If we're representing methane as a spherical molecule, which is what we do in SpeedMD, then if we go to a packing fraction that's greater than 0.494, we know that's the end for the liquid. And so this is essentially getting up near that kind of packing fraction. For methane, the packing fraction is roughly equal to the mass density. So that's why this curve is kind of sharp here, even though it's a sphere. As we go to ethane, we can see that we go to higher densities before we reach that jamming limit. And as we go to higher and higher densities, we can see we're reaching a kind of a universal jamming limit up in here, okay? Somewhere around 0.9, which roughly corresponds to the mass density of amorphous polyethylene. Makes sense. Another thing that we can see is that as we go to longer chains, it's clear that the intercept here is getting smaller for C30 than it was for C1, C2, C3. Let's take a look at just that y-intercept. And that's what I've done here. And I've plotted it versus the chain length. You can see that methane's a little bit out of line, but it doesn't have the same diameter as the rest of the molecules in the chain. Okay, so don't be bothered by that. So for the other elements of the chain, we can see that this intercept, you can even see it here, that it reaches a plateau here, and then it expands down, okay? But it's a little more complicated than that, because if you're thinking three-dimensionally, the methane is closest to you in 3 dimensions. The ethane is a little bit further behind and shifted to the right. And then all of these things are kind of curving back and down into the plane of the paper. And so the C30 is the one that's furthest away from it. And the reason I like these colors and I like this graph is it kind of reminds me of a rainbow. And so in my wall of favorite graphs that I've ever made. This is definitely one of them. So it's pretty to look at to me, and it has a kind of an interesting physical meaning. And the most important one to think about for now is, what is this low density limit doing? And what you can see is that as you go past about hexane, so think 0.2 on this scale is hexane. So hexane, heptane, going on up, okay? As you go further up the scale, you can see that this thing is dropping to the -1 power. What is this -1/6 power? What does that mean? Well, if you pretend that everything is a sphere and you equate the volume of an N-alkane to the volume of a sphere, you come up with a diameter of that sphere. But we also know what the M effective is for that chain in, let's say, Saft space, right? So let's plot log of M effective on this scale, and then what does the effective volume of a sphere do as that molecule gets bigger in volume, okay? What you calculate is that goes to the -1/6 power. And you can see that doesn't make sense if you go past hexane, all right? And so what it means is, if this line was shifted down, let's say, to right here, it would make things hard to see. That's why I put it up there. Then we could be a little bit low for the methane, ethane, propane, be a little bit high for pentane, hexane, and then forget about it. We'll just be wrong for these other molecules, okay? And we're just being fitting data to make the parameters do what we want them to do. And you could get away with that. I mean, even benzene is not that far from hexane, so, and it's more roundish, like a hamburger. So fine, we can do that. But it doesn't make sense if you think about the polymer limit. In the polymer world, it's well accepted, well established that the viscosity, the diffusivity, all of these things decrease with 1 over the molecular weight. And that's just till you get to the entanglement regime. Okay, so once you get to the entanglement regime, it goes as 1 over molecular weight squared. So this 1/6 thing is not making a lot of sense. And it's not that difficult to develop a generalized correlation for all the N-alkanes. So this whole curve, whole set of curves here, is characterized by this set of parameters, where this C parameter is just this exact limit. And we can make a very simple approximation for how this glass transition density is occurring. And you see that it goes to a finite number as we go to infinite chain length. Next question is, remember, all of our molecular simulations were just for the reference contribution, because that's the way SpeedMD works. You just simulate the reference fluid and you calculate the other properties through some kind of perturbation theory. So our hypothesis was, let's take our diffusivity of the fold divided by the diffusivity of the reference and perform a perturbation series in 1 over temperature to figure out what the attractive effects must be. And we got some results, okay? So this is what we get. So for for spheres and things like that, just the simulation was pretty close to the data, because the data are mostly at high temperatures where the attractive effects are minimal, right? So at room temperature, you're at a reduced temperature of 1.5 or 1.8 for methane. So if you're just measuring diffusivities at room temperature, you're not going to see a lot of attractive effects. If we want to do a better job, then we have to incorporate those attractive effects, and you can see that these lines go through these points, and that's what this correlation was about. But if you look at this number, 0.55, compared to 3.3, it's a little bit odd that the first order term is much smaller than the second order term. And in fact, I have to admit that the grad student, Nevin Garrick, said, you know what? I don't think we need this term because I can throw it away and get practically the same results just with this term. And maybe we could add a cubic term. And I said, no, don't do that. How would that make sense? You can have a perturbation theory that ignores the first order term. Let's think about that in the context of entropy scaling. What does entropy scaling do? Well, we know that the Helmholtz energy goes as a perturbation series. We know that the internal energy goes as a perturbation series. What happens when we rearrange that and get the residual entropy in terms of this perturbation series? Do you see that the t squared term, or the t 1 over t term, disappeared? That's what residual entropy scaling does. So you're just skipping this first order term in temperature. It's just a end around way of making that happen. So is the reason that entropy scaling is working just because it omits the 1 over t term? Or is there something more fundamental to it than that? At this moment, I still consider that to be an open question. There's another problem that we really didn't do a good job with when we were developing our attractive correction. And that is our attractive correction sort of just adds systematic shift in the effect of the attractive terms. But what the data say, and the Leonard-Jones model does a good job of representing this, is that it becomes more concave down as you lower the temperature. So in the middle, things aren't changing all that much, but on the ends, it's changing a lot. And so that's something that you pick up when you use the Leonard-Jones fluid as your basis of your corresponding states or your entropy scaling or whatever you're using. And so that's something that needs to improve. And so if we would do more molecular simulations, and hopefully for non-spherical molecules, we need to do a better job of what's happening in this low density range. That ought to be a straightforward process. And so that's going to be one of my recommendations. Getting those kind of data experimentally, I have a feeling that's complicated. But to do it from simulation, I think that should be straightforward, and that will teach us about the physics. So what does the LSM model look like? You can see that it's also got this 1 minus density over the glass transition density in it. Okay, so it's got that effect incorporated into it, so it's a free volume theory. And as far as the temperature effect, it's only this exponential of 1 over temperature. And so then there are some nuances with respect to what you choose for the effective Leonard-Jones dynamic. Interesting thing I decided to do was when Bell developed his model for the Leonard-Jones spheres, I plotted a parity plot for his results versus the simulation results of Bidakov. And wow, he's doing pretty good. That's good parity. And I said, well, why not do the same thing for the LSM model? And it's not so good. So it says that this LSM model is not really a great model, even for Leonard-Jones spheres. But when you let this number and that number and this number be, and this number for the hard spheres all be adjustable constants, then you can get something that works. Okay. So let's talk then about a generalized residual entropy model. We don't really know who's right, Sugatov or Rosenfeld. So let's put in a parameter. If that parameter is 0, Sugatov is right. If that parameter is 2/3, Rosenfeld is right. Then we'll let the data tell us who's right. Similar question is there an interaction effect of residual entropy and temperature? So we've got a temperature effect here already in the low density limit. This question is saying, as we go up to higher densities, do we need to have a different temperature effect to account for that? That's an open question. This polynomial in residual entropy is just kind of standard. And here's this generalized expression for the log of the self-diffusivity. In order to do the analysis, I'm going to use the RMS log deviation, okay? If you use MAPE, because you can never have less than negative 100% error, okay? But you can still have positive 300% error, you tend to bias your results in situations where you can have large errors, which you can for diffusivity, because it's varying on a log scale or an exponential scale, okay? So if that's the case, then this MAPE will give you a bias towards the negative estimates. And that's not what we want. We want to be fair to negative deviations are just as bad as positive deviations. Okay, so what we want is an unbiased estimate. And so that's why I'm going to use the log deviation. And note that if the deviations do get small, then the log deviation becomes the MAPE because of the way log 1 plus x is. Okay, then instead of using maybe an F test or something like that, what I'm going to use is this thing called BIC. And it's a very simple adjustment to the RMS log deviation. All we have to do is put it into this formula. And what it does is it penalizes the RMS if we're just throwing in extra parameters without really improving the log deviation. So it's just a penalty function essentially for adding too many parameters. And this comes up in the context of what's called a parsimonious model. I just learned this vocabulary word this summer. I'd heard of it before. Generally, it means stingy. I think it derives from the scenario where whoever can slice the cheese the thinnest, you know, so if you can get 1,000 slices of cheese out of 1 pound, you can feed 1,000 people, I guess. So it's not necessarily a compliment. In this context, though, I think it is a compliment. So in this seminar or lecture that I went to at the Midwest Thermo Conference, there was a guy speaking there who talked about using this parsimonious concept in the context of machine learning. And what they did was they took the trajectories of all the planets and stars that they could measure over 1,000 years or something, and they just fed them to a machine learning model and said, come up with a parsimonious model. Don't just fit 10,000 parameters to this data. Develop the model that most succinctly represents these data. Didn't tell it anything about what that model should look like. And out popped Newton's laws. So I was impressed. One equation, no parameters, F equals ma, all the data. That's a good model. Okay, and so if BIC can help us get to that, I want to use BIC. So here's our general model. I just wrote it at the top of the page here, just a reminder of what it means. And then for alkanes, my supposition, this is just the regression of the molecular simulation results. This is just what it looks like. And so I'm just going to take that as my baseline for the hard chain limit, not the hard sphere limit, as at 0 density. So I'm getting away from this Chapman-Enskog trap. I'm going to have a generalized correlation for the way that this attractive energy scales. And we should expect that there should be some kind of smooth function that describes that attraction as we go longer and longer in the chains. And similarly, I'm going to have a generalized correlation for this xi function, the scaling function, as a function of the number of carbons in the chain. And if I start by just treating all these parameters, I've got about 9 minutes, I think. Is that right? So anyway, that's what I'm aiming for. And so I have the full model where I'm including xi naught, xi1, xi2, tau1, tau naught, and this coefficient that represents the interaction term, and this ds that tells the difference between Zugatov and Rosenfeld. So let's take a look at that Zugatov-Rosenfeld parameter first, and let's see what happens. What we're going for is the smallest BIC wins. What we see is when we wipe out that ds term and just set it equal to 0, we get a slight improvement, right? Because we have fewer parameters, and we're getting pretty much the same deviation. So BIC says that's a better model. When we eliminate that degree of freedom and say, oh, it has to be 2/3, instead of going down, the BIC goes up very badly. All right, so that's the end of the Rosenfeld scaling. What if we eliminate this coefficient of the interaction term of temperature? We actually get a better model. The RMS goes up a little bit, but the benefit of setting another parameter to 0, the BIC says that's worthwhile. If we were to try to use a universal value for tau, so just tau naught, no adjustability as a function of the chain length, that's a problem. BIC goes up. If we try to change this Xi2 parameter, okay, that's a really bad idea, okay? So, and if we ignore all three of these adjustable parameters and just use a kind of a universal alkane, that's not a good model either. So what we come down to is this interaction effect and Rosenfeld scaling are bad ideas. So let's just ignore those now, and this will be our generalized alkane model. Let's take a look at how that is now. These are then the coefficients of the polynomial. This is the general correlation then for the attractive tau at the low density limit. And this is the correlation for our scaling parameter smoothly as a function of chain length. And we don't really see any kind of systematic trends in our residual log deviations. And we get something that doesn't look too bad going all the way out to hexacontane. Now, the data for hexacontane are not very plentiful. So you can see there's just this, and this, some plus signs right in this range. So we don't have a huge amount of data for that, or for C30. For propane, we have a lot of data. But even for propane, we don't have much data at low density. And so this is a bit of a problem that we should think about how to solve using molecular simulation. I think molecular simulation can help us learn the physics here. What happens when we extend this approach to every kind of molecule, non-alkanes, but not hydrogen bond? Well, we can ask the question, do we need to include tau and P3? Do those really help us in a significant way? Let's ask that question first with regard to the N-alkanes. And so we have this generalized correlation, but if we have some data that are specific to one alkane, will it help us to regress, to add these parameters and regress something customized for that N-alkane? And for tau and P3, it says yes, we should probably do that. But for the Xi, the scaling parameter correlation for N-alkanes, you don't need anything. That scaling correlation is good enough, and the best you're going to be able to do, even though your MAPE is smaller, you're adding more parameters, and so your BIC is going up. So your best parsimonious model is going to be just adding tau and P3. When it comes to the non-alkanes, you know, that scaling correlation for N-alkanes, it's just not good enough. And so it's not effective to say every molecule in the world is just an effective N-alkane. So you need all three of the parameters in that case. So that leads to a summary of when we use this generalized residual entropy approach. We end up with 3 parameters per molecule, for non-alkanes at least. And that compares to 2 parameters for the LSM model and 5 parameters for this DGJ, this model, that imposes the Rosenfeld scaling. So it's kind of interesting that a model with more parameters that has the wrong scaling can't keep up with a model that has the right scaling. So that's kind of the general conclusion. When we want to make some extensions to hydrogen bonding molecules, there are some results for viscosity. And so I expect that the analysis of self-diffusivity will go in a similar direction. And so what we see in viscosity cases, the shapes of these curves change a little bit, especially as we add hydrogen bonding, they curve upward more. For long chains, it's flatter. And for the quantum fluids, it's again kind of like the way that the hydrogen bonding fluids behave. It curves up more. So probably that's what we might expect to see with self-diffusivity, and then we'll have to come up with some explanations of that. So this brings me to the conclusions. I'll just briefly say that the Zugatov scaling seems to fit the data the best, and the 5-parameter model is not as accurate, probably because it has that implicit Rosenfeld scaling. The difference between the 3-parameter GRE and the 2-parameter LSM, pretty small. And so I wouldn't say that GRE is better than LSM. If we want to start thinking about how to build generalized models that have better physical basis, I think we need to start focusing on the negative concavity, especially at the low density end. That ought to be something that's straightforward to do. We can also get second virial coefficients out of that, and maybe the attractive part of the second virial coefficient and the attractive part of the self-diffusivity, maybe those can be correlated together. Maybe they do what they do for similar reasons. And so there's some hope there, and that's in some ways reflected in the plus scaling and the way that they use the second virial coefficient there. So I think that there's some interesting possibilities there. And the key thing is we need more data. So if you look at this conclusion slide, a lot of what you'll see is we need more data. There's not enough experimental self-diffusivity data. There's about 2,000 points at all state points and all molecules. And so we need more experimental data, we need more simulation data, and we need, especially for hydrogen bonding systems, the data are especially sparse. I found some data for out to decanol, but just like we saw for hexacontane, the data get very, very limited in range as we go to higher and higher chain lengths of alcohols. I'll just conclude with one more adventure and sort of lay out some possibilities here. If anybody is interested in this sort of thing, I'd be happy to talk more about it. And that is the actual final chapter in PGL was about surface tension. And we didn't get to look at classical DFT. I would love to be able to evaluate that. Fortunately, Gustavo Chaparro and Andre Mejia have developed this SGTPy method. It stands for Square Gradient Theory in Python. And Gustavo's been very helpful to me to learn how to implement and run this code. And in the process, I've gone ahead and added this ESD MEM2 method to this SGTPy code. So if you were waiting until the Python code came out for the ESD method, it's out. I'll be happy to send it to you. And one of the benefits of that is when you look at this SAFT VR and SAFT gamma me, they're somewhat limited when it comes to the number of compounds that they've got characterized. especially if you're talking about the associating compounds. They do have a corresponding states method for just predicting these SAFT VRMe parameters. They call it bottled SAF for 8,000 compounds, but I don't think anybody's going to be surprised if a corresponding states method for predicting those parameters doesn't give you great accuracy. So I think you're going to need something a little more sophisticated, and so until we get a broad range of characterizations for those kinds of models, I think we need to. One second. Okay, so sorry about that. And so if you want to have enough parameters for enough compounds to evaluate a significantly large database, these two models might be somewhat limited. But if we have the SD model, and it has essentially, I can explain later why I think it is, but infinite number of compounds. You got a compound, you want it to have ESD parameters, send me an email, I'll get them right back to you the next day. All right, so this is something more about the adventure continuing, and I hope to report about that in maybe a year or so, maybe 6 months. So I'll wrap it up there and take any questions. Thank you.